Good afternoon, everyone. I just want to adjust my camera quickly and see whether it's streaming. Okay, it's streaming now nicely. I want to see whether the sound is, okay, the sound is being picked up. Now I just need to move my camera. Okay, there we go. Put me right there in the corner. Okay, the most important part is the work, not me. Okay, so here we have everything is now beautiful. We are doing chapters 34, 35, and 36. This is usually done as a combination of chapters, and it all deals with optics. Okay, so let's look at our first problem here. Okay, we have, we are not going to dilly-dally. Okay, this is question number one. We have a 100 kilowatt radio station. So we have a 100 kilowatt radio station that emits EM waves in all directions. So in a spherical, like tangential, perpendicular to every point on a sphere, so in all directions, it is emitting electromagnetic waves in all directions from an antenna on top of a mountain. So it's on a mountain and there's an antenna. They are asking what is the intensity of the signal at a distance of 10 kilometers. So intensity of a signal. So how do we calculate the intensity of a signal, of an EM signal? So the intensity of an EM signal, excuse me, is equal to the power divided by the area. That is the intensity of a EM signal. Okay, now this is the definition of intensity. It is power divided by area. Okay. Now what's the power that they give us? Okay. With what power does this radio station produce these EM waves? Okay, and that power is 100 kilowatts. Okay, so that is 100, and kilo is 1,000, so 100,000 watts. So 100,000 watts. Now, what is the area? It is in all directions. So the area is a sphere. Okay, so it is the surface of a sphere since it's in all directions. So what's the area of a sphere? Let's look at the area of a sphere. The area of a sphere can be calculated as 4 pi r squared. Okay, that's the surface area of a sphere. Okay, now let's just plug in. This is still 100,000. Now let's plug in 4 pi. What is the radius of the sphere? The radius of the sphere is the distance at which we want to know the intensity. Okay, and that is 10 kilometers. Okay, so 10,000 meters, and you need to square that. Okay, you need to square that. And if my math is correct, you will end up with a power of, or rather an intensity of 7.96 times 10 to the negative 5. This is in meters, by the way. That's in watts. This is in meters. There's a small m there. And this will be watts. And that meter is square, watts per meter square. So it's 7.96 times 10 to the negative 5. 7.96 times 10 to the negative 5 watts per meter square. Okay, let's see if there is an option for 7.9 times 10 to the negative 5. 7.9, nope, there is no 7.9 times 10 to the negative. But if you simplify 7.9, it becomes 8 times 10 to the negative 5. Okay, they just rounded up. Let's check this one. 8 times 10 to the negative 5 watts per meter. Let's see if it's correct. And yes, it is indeed correct. Okay, that is wonderful. Now let's go. These are, by the way, elementary questions based test on what you know so far about optics from school. So, question number 2. Okay, an FM radio station broadcasts at a frequency of, so the frequency is equal to 98.6 megahertz, that is times 10 to the 6 hertz, if I'm not mistaken, and 8.6 million hertz mega. What is the wavelength of the radio waves? Now, how do you calculate the wavelength of an EM wave? The wavelength of an EM wave is simple. Lambda, which is the wavelength, is equal to the speed of light divided by the frequency of that wavelength. So let's calculate that. The speed of light, as always, is 3 times 10 to the 8 meters per second. Now, some people use 2.999. We just use 3. And then the frequency is, let's see, what's the frequency? 98.6 times 10 to the 6 hertz is per second. So per second. Now, if you flip this up, the answer, if you do some a bit of dimensional analysis, your answer will be in meters, which is what we want. We measure wavelength in meters. And 3 times 10 to the 8 divided by 9.8 times 10 to the 6. If you divide these two, you will get, it's 98, right? Yes, that is 98.6. And if you divide this, you get 3.04 meters. Okay, this is just simple. I'm not going to plug this into a calculator and show you how it is done on the calculator itself, because it is just dividing these two quantities. This is something you've been doing since uh, grade 10 in physics, if you have had physics. If not, then basic math. It is just knowing this formula. Okay, now question number 3. Let's look at what question number 3 requires of us. What does question 3 want? What does question 3 want? Okay, first of all, it says a spherical particle. This is a problem where I have, this is the one where I have a problem. I had calculated an answer which does not agree with the answer that has been given or provided here. Okay, I do not get this answer, but I'm going to talk you through it as to how I got to what I got. First of all, they tell us a spherical particle of density rho is 5 grams per centimeter, square centimeter. So first of all, square centimeters is a unit of area. It's a unit of area. So this is why I had my problem, but I saw in other books that they also write the square centimeter. So I might be wrong in this case for this. Okay. And then so I use the density as is, although I am not convinced that it should be per square centimeters. And then it has a 2 millimeter radius and is located at a distance from the sun. It's the same distance from the sun, which is 1.5 times 10 to the 11 meters. And then they tell you that the gravitational constant G is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And then, of course, S, which is the average intensity or distance, I think 1365, and then that's the average intensity 1365 watts per meter squared, like we just calculated in intensity the first question. And then ms is the mass of the sun, 1.9 times 10 to the 13. Now if the particle absorbs 100% of the sunlight reaching it, the ratio of the force exerted by the solar radiation to the force of gravity exerted on the particle by the sun is, so we need to calculate the force of, the ratio of the force of solar radiation to the force of gravity. Okay, so Before we can do the ratio of the forces, let's just calculate the forces first. Okay. Now I told you before, I do not get the same answer as this, and I've checked, and uh, this is for according to what you should know. I'm just going to show you the formulas and how to calculate them. The ratio I get is much different. Okay, so let's look at first. Let's calculate the force of radiation. Okay, the force of radiation due to the sun on this particle. Okay, what did it say? A spherical particle. It has a density of rho, 2 millimeter radius, and it is the same distance from the sun as the Earth. Now, let's calculate the force that the sun, the force that radiation imparts or is imparting onto this particle. Okay, now the force of radiation is equal to the intensity times the area divided by the speed of light. Okay, that is how we would calculate the force of radiation. Okay, so now this is the average intensity. Okay, this is the average intensity. And the average intensity in this case has been given to us as 1365. 1365. That's the average intensity, 1365. Multiplied by, that's watt per meter squared. You multiply that by area. The area is the cross-sectional area of this particle. Okay, it's the cross-sectional area of the particle. Now the cross-sectional area of a sphere is a circle. If you cut a sphere in half, its cross-section is a circle. So the area for the circle would be pi times the radius of the circle. And they give us the radius. It has a 2 millimeter radius. So 2 millimeters, 2 times 10 to the negative. Okay, let me rather just write it in terms of, so it is pi times the radius squared, and the radius is 2 millimeters, so 2 millimeters is 0, 0.00, it's 1, 2, 3, 0, 0.02 squared, and then that. Let me see if it all fits. Yep. You square that, you multiply all of that, and you divide it by the speed of light, of course. 3 times 10 to the 8 meters per second. Okay. Now, if you do all of this, okay, now I have here 365 pi, 1361 in my old problems, but it's been upgraded to 1365 as the average intensity. So let's calculate it there. Let me just pull up Desmos, the calculator. There is one there, but I'm going to show it there. Just the Desmos calculator, there it is. Okay, what we are going to be doing is, where is it? There, fraction. So it's going to be 1365. So I can show you exactly what I did to get this answer. And it's multiplied by pi, and then multiplied again by 0, 0.02, 0.02 squared, and then all of that over 3 times 10 to the 8 meters per second. Where is the exponent? Let me just see. Functions, e, pi, log, n. Keep forgetting. ABC, main. There should be an e here. Okay, let me just 300 million. Okay, let's see. 300 million. Yep, there it is. 3 times 10 to the 8. And the answer that I get for the force of radiation is 5,7. And you all can see that the answer that is been given. Okay, it seems that you can't see. Mm. But the answer that I get, I'm going to write it down here. 571 times 10 to the negative 11. Okay? That's the force of radiation. Now that's the force of radiation. Now I've calculated the force of radiation. Now let's calculate the force of gravity. Now I'm going to write this down. The force of radiation, 5,71 times 10 to the negative 11. Okay? And I did this individually. They did and simplified the formula, so but I did it individually. Okay. Okay. Now let's calculate the force of gravity. If G, of course, is big G times the mass of 1 times the mass of divided by the rate distance between them squared. In this case, big G is 6,67 times 10 to the negative 11 multiplied by the mass of the sun, which in this case is be given by 1,99 times 10. Let me rather move this whole thing because I see I'm going to run out of space. Let me start here then. FG, right smaller. Do I have that whole space there? And this is G, the constant, 6,67 times 10 to the negative 11. Then we have the mass of the one part is the sun, because the gravitational force between the sun and this particle. So the mass of the sun is given as ms. It's 1.99 times 10 to the 30 kilograms. Remember, it was in SI units. Now we need to calculate the mass of this particle. Okay, how do we calculate the mass of this particle? Okay, now we have been given the radius of this particle, so we can calculate its volume. Okay, and from that volume and density, we can calculate its mass. Okay, because mass, remember, mass is nothing but density is mass over volume. Therefore, density multiplied by volume should be equal to the mass. Okay, and the distance between them is 1.5 times 10 to the negative, or rather 11 meters. Okay, so now I did do this on a separate piece of paper. Now let me rewrite all of that. First, I'm going to fill in the math. Let me just rewrite everything as E, 6,67 times 10 to the negative 11. Here we have 1,99 times 10 to the 30. Then we have the distance 1.5 times 10 to the 11 meters. Now, as for the density, it will be a simple, let's just see so I can show you. Here we go. The density is 5 multiplied by the volume of a sphere. Let's just check. What is the volume of a sphere? They tell us here it is a spherical particle. So volume of sphere. Volume of a sphere. The first thing, the volume of a sphere is 4 over 3 pi r cubed. So 4 over 3. Where is it now? That's 4 over 3. Fraction. 4/3. Okay, let's leave it at the end. Pi multiplied by pi. 5 times pi times the r squared. The radius in this case is 0,002. That's cubed. Radius cubed times 4 over 4 divided by 3. 4 over 3 pi r squared. So that should be, which gives us an answer of 1,6 times 10 to the negative 7. Okay, so there we have this value 1,67. 1,67 times 10 to the negative 7. Okay, let's clear that. And let's do this then. Now let's calculate. Let's see if GeoGebra, okay, it has a better quality calculator. Okay, here we go. So we have on top, let me just do it like that. And I want to just check something before I also type it in. On my calculator, I have the actual scientific calculator here. Let me just show you. I'm using this calculator here. Okay, so it's 6.67 times 10 to the negative 11 multiplied by 1,99 times 10 to the 30 multiplied by 1,67 times 10 to the negative 7, and then that answer, if you multiply everything on top, you should get 2,216 times 10 to the 13. Okay, that makes sense. It's negative 11, that's negative 8. 30 minus negative 8 is, and then of course the whole multiplication to the bottom. If divide that 2,216 times 10 to the 13 divided by, did I forget to square here? Shouldn't there be a square here? Yep, it's distance squared. R squared divided by 1.5 times 10 to the 11 squared. Now I get the force here. Let me just rewrite the whole thing. That should still be a square. That should be a square. The answer at the end for the force of gravity between them is 9,85 times 10 to the negative 10. Okay? There's the force. 9,85 times 10 to the negative 10. Here is where I get a different value from what the actual answer is. Okay? Now I've spoken to colleagues about it. The correct answer should be 1,75 times 10 to the 4, but I do not get that answer. Okay, but you first have to calculate the force due to the radiation, and then the force due to gravity, and then find the ratio between those two. Okay, now if you were to find a ratio between those two as is, uh, you will get a number that is not in one of those values. Okay, so let's go on to question number 4. So I did not leave it out, I just did it the way I would do it, but I did not get the same answer. Okay, question number 4. At a distance of 10 kilometers from a radio transmitter, so a distance from 10 kilometers from a radio transmitter, the amplitude of an electric field is zero point 0.2. So the amplitude of an electric field is zero point 0.2. Now this is where it gets fun. This is the questions that you have to answer in the exam. Now at a distance of 10 kilometers from a radio transmitter, the amplitude of the electric field is zero point 0.2 volts per meter. So the E field, the amplitude of the E field, so the amplitude of the E field at a distance 10 kilometers from a radio transmitter is zero point 0.2 volts per meter. Okay, what's the total power emitted by the radio transmitter? Now, what's the ratio between the power and the electric field and distance? Okay, now total power, you know, or you should know, total power is equal to the intensity multiplied by the area. Okay, total power, this is total power, is intensity multiplied by the surface area. Okay, surface area. In this case, it is spherical in nature, so this is surface area. So it should be intensity multiplied by 4 pi r squared. Okay, so intensity multiplied by 4 pi r squared. Okay, now we know what the total power is, how to calculate the total power. So let's first calculate then what is left, the intensity. First, let's calculate intensity. How do we calculate the intensity from a radio transmitter? Okay, now the intensity is equal to a half times the speed of light times E naught times the electric field amplitude squared. Okay, so it will be a half times the speed of light. 3. These formulas, by the way, are in your so intuit, I should think. 3 times 10 to the 8 times the permittivity of free space, 8,85. Then the reason why it's permittivity and not a permeability is because it's an electric field. The electric component of an EM wave, 10 to the negative 12. And then E naught, in this case, is zero point 0.2, and you square that. Okay, let me see if everything shows up there. Okay, beautiful. Now, if you were to calculate this, a half times 3 times 10 to the 8 times 8,85 times 10 to the negative 12 times zero point 0.2 squared gives you an intensity of 5,31 times 10 to the negative 5 watts per meter squared. Remember, our very first problem was on intensity, and this is what we measure intensity in, the amount of power per unit area. Okay, power per unit area. And that makes sense. Okay, intensity is power per unit area, so we want the total power. So in that case, we have defined intensity. Intensity is defined, remember, as power per unit area. So if we want the power, we have to multiply intensity by area, and that is what we do here. The total power is intensity multiplied by area. Okay, I hope that makes sense. So we have now calculated the intensity. Let's calculate the total power. The total power. So it's intensity multiplied by the area. In this case, it is 4 pi r squared. So the intensity we just calculated is 5,31 times 10 to the negative 5. That's the intensity we just calculated a few minutes ago, or a few seconds ago. Multiply by 4 pi times r. In this case, what is the radius? It is the same distance that has been given to us. That's the radius, because it goes in, all the EM wave goes in a spherical direction, which is in all directions. Okay, so 10 kilometers. So 10 kilometers is 10,000 meters. That should be squared. 4 pi r squared. And if you were to calculate all of that, that squared is 100 times 10 to the 6, of course, if I'm not mistaken. Yes, 4 pi, all of that, you get 66,7 times 10 to the 3 watts. So 66,7 times 10 to the 3 watts, or just rather 66,7 kilowatts. That's the total power that is emitted by the EM transmitter. Okay, let's check if there is an option for 66, 67. 66.7 is rounded up, is just 67 kilowatts. And let's check, yes, 67 kilowatts is indeed correct. Right? Question number 5. Question 5. Find the force. Find the force exerted by reflecting sunlight off a reflecting aluminium sheet in space if the area normal to the sunlight is 10,000 square meters and the solar intensity is 1,350 watts per meter. You have seen this number, it was 1,356. Different textbooks have different values for solar intensity. Okay, so they want the force exerted by reflecting sunlight. So how much force when sunlight hits this aluminium sheet? Okay, it bounces off, it reflects off, but it does exert a force on the reflective sheet. With it bouncing off, it exerts a force. Okay, remember Newton's third law: for every force there is an equal but opposite force. Okay, so it creates a force because it is reflected off. It does impart a small bit of force. Now, that force is due to radiation pressure. Okay. Now the force is due to radiation pressure. So how do we calculate radiation pressure? Radiation pressure, P rad, the radiation pressure is equal to 2 times the intensity divided by the speed of light. Okay. 2 times the solar intensity. In this case, it's the sunlight's intensity, the solar intensity. Now, how do we calculate force? Force is related to pressure. In this following scenario, force is equal to pressure times area. This is force. Remember, we define pressure as force per unit area. That's pressure. So therefore, it makes sense that pressure times area should be force. So this force that we want, this radiation force that we want to calculate, is equal to the pressure, but in this case, it's the radiation pressure multiplied by the area of this sheet. Okay, so the radiation pressure we've already said is equal to 2 pi 2I rather c 2ic, at the speed of light there, 2I divided by the speed of light, so 2 times the intensity divided the speed of light times the area. Okay, so if I rewrite this in the next line, force therefore is equal to 2 times the intensity divided by times the area divided by the speed of light gives you the force. Okay, now we know that the intensity, solar intensity, is equal to, so it's 2 multiplied by the solar intensity. In this case it is 1350 watts per meter squared. That's the solar intensity. The area they give us as 10,000 meters squared, 10,000 meters squared, divided by the speed of light of 3 times 10 to the 8 meters per second. Do a bit of dimensional analysis. That cancels, that cancels. It's watt meter per second. And that all, I just checked, 10,000, 3 times 10 to the 8. This is approximately 0.09 newtons of force. Okay, so 0.09 newtons of force that the solar energy or the sun is imparting onto this plate. Okay, now let me check something, or rather, you can calculate how much newton. It's difficult to visualize a force, but if you take this force and you divide it by 9,8, that should be the mass that you need to hold up to feel that force. So it is 0.09 divided by 9,8, and that mass you get is the amount of mass that you will say you'll need to hold up to exert that type of force. Okay, if you want to experience what that force is, 0.09. Let's check if there's a 0.09 there. Got my eye immediately. So 0.09 newtons of force is imparted from the solar radiation to this aluminium sheet. Okay, now question number 6. Question 6. They tell us if the radiant energy from the sun comes in as a plane EM wave. Okay, so the radiant energy from the sun comes in as a plane electromagnetic wave. Okay, of intensity 1340 watts per meter squared. So the solar intensity is 1340 watts per meter squared. Calculate the peak values of E and B. Okay, now peak values means the maximum. Okay, the maximum electric intensity and the maximum, not the electric intensity, like the maximum electromagnetic, the maximum electric value. The peak, okay, let me just say this. The electric peak is E max and the magnetic peak is B max. Okay. Now, the intensity of an electromagnetic wave is related to the maximum. You have seen this formula before. You should have. Is related to the maximum intensity of the electric component in the following formula: a half times the speed of light times the permittivity of free space times E squared max. This is the peak, the maximum value. Okay, calculate the peak value. This is the peak value for the electric component. Now to find E max, if you make E max the subject of this formula, if you make E max the subject of this formula, if you make E max the subject of the formula, you get the following formula. It should be I divided by all of that, or divide by a half, you simply multiply by 2, C, permittivity of free space, and then the square root of all of that will get you your peak electro electric component, your peak electric value. Okay, electric component value. So if you substitute in all the values, let's substitute in all the values into this formula. It's 2 times the intensity is given as 1340. The speed of light is 3 times 10 to the 8. And then the permittivity of free space, 8,85 times 10 to the 12, negative 12 if I'm not mistaken. Yes. Therefore, the peak value for Emax, therefore Emax is equal to, it has a peak value of approximately, okay, this is a rounded value, 1005 volts per meter. That's the peak value for electric component of this EM wave. Okay, so the peak value is 1005 for the electric component. Now let's calculate, by the way, this formula is in your book. And then, of course, this formula, Emax is related to Bmax as follows. Emax is equal to C times Bmax. Okay? Emax divided by Bmax should give you the speed of light. This is one of Maxwell's derivation, conclusions of that Einstein did. He showed that, or rather Maxwell showed it first, that the speed of an EM wave should be specifically just c. Okay, so to find Bmax, okay, you just take your Emax value and you divide it by the speed of light. These formulas, by the way, are in your book. So Emax divided by the speed of light. Emax we just determined is 0.005 volts per meter divided by 3 times 10 to the 8. You get 3, check the difference, Bmax is 3,35 times 10 to the negative 6 Tesla, while Emax, the electric field value, is much larger than there. In fact, it's 3 times 10 to the 8 times larger than, and that will always be the case. The electric field, the maximum electric field value will be 3 times 10 to the 8 times larger than the maximum magnetic field value. Okay, now let's check. 1005 we got, remember? So the closest one there for the Emax is 1000. And then of course we got 3,35 times 10 to the negative 6. And that's what they got as well. So we'll pick this one, and yes, 1000 volts per meter and 3,35 times 10 to the 6 Tesla. Okay, so we did calculate the peak values for the electric field and of course the magnetic field. Okay, so question 7. Question 7. The intensity of radiation reaching the Earth from the Sun is 1350 watts per meter. So the intensity of the solar radiation is that value. The Earth's radius is 6.4 times 10 to the 6 meters. How big a force does this radiation exert on the Earth? Okay, so how big a force? We just had that formula. Okay, how big a force? So force we calculated or determined earlier is just the radiation pressure multiplied by the area of whatever you are shining the EM waves on. Okay, so the radiation pressure we determined earlier on. Now, since the radiation is all absorbed, we can calculate the radiation pressure. By the way, this is another way you can deal with the previous problem. The radiation pressure can be calculated as the intensity over the speed of light. Remember earlier on, how did I calculate the radiation pressure? It was in one of my problems here. I calculated the radiation pressure 2I over C. That's for a perfectly reflecting sphere. Now for a perfectly absorbing sphere, the formula changes to, for a perfectly reflecting sphere, the radiation pressure, let me just write it here in the margins. The radiation pressure for a perfectly reflecting sphere like we had earlier is 2I over C. Now the radiation pressure for a perfectly absorbing sphere like the Earth is in this case, it is not really, but for in this case, that is I over C. Okay? Just don't get that's for perfectly reflecting and this for perfectly absorbing spheres. Okay, so we have the radiation pressure for perfectly absorbing sphere times the area of a sphere, which is 4 pi. The cross-sectional area, which is pi r squared. Cross-sectional area because remember, even though it may be a sphere, we are just looking at a cross-sectional area of this thing. So the intensity is 1350 watts per meter squared. The speed of light is 3 times 10 to the 8. We multiply that by pi times the radius of the Earth, which in this case, did they give us the radius of the Earth? 6.4 times 10 to the 6 meters. We square that, multiply that by pi, multiply that whole bracket by this radiation pressure answer, and we should get approximately 5.79 times 10 to the 8 newtons. Okay, and that is what we got, 5.79, or rather 5.8. 5.8 times 10 to the 8 newtons. That is the radiation pressure. If the Earth is a perfect absorber of solar radiation, that's how much force is on the Earth. So every time the sun shines, in this case, it imparts that force to the Earth. Okay, now question number 8. Accelerating charges radiate EM waves. Okay, so accelerating charges radiate EM waves. Calculate the wavelength of radiation produced by a proton of mass mp, which is just m, moving in a circular path perpendicular to a magnetic field of magnitude b. Okay, now this is a problem where you need to follow the math in symbol form. Okay, now the magnetic force on the proton, the magnetic force on that proton provides the centripetal force that is needed for the circular motion. Okay, so that magnetic force. Now the magnetic force B, you remember the magnetic force on the proton, but they tell us it's moving in a circular path perpendicular to a magnetic field of magnitude B. Now this magnetic field is providing the force that is providing the magnetic field is providing the centripetal force. Okay, the magnetic force is the centripetal force for that particle to move in that circular direction. Okay, now this magnetic force, the force of magnetic, let's just say FB, the magnetic force is equal to, from your studies on magnetic fields, QVB, the Lorentz force, isn't it? Since the velocity in this case is perpendicular to the magnetic field. Okay, they tell us that it's moving in a circular path that is perpendicular to a magnetic field. So that is the magnetic force. Now the centripetal force, we know that centripetal force This magnetic force is providing the centripetal force to move it in this direction, right? The circular path. Now, the centripetal force, we know from our first uh, semester on mechanics, centripetal force is mv squared over the radius, right? Where r is now the radius of the circular path. Okay, r is the radius of the circular path, m is the mass of the proton, and v is its velocity. Now, if you were to simplify this, remember the centripetal force is provided by this magnetic force. So Fc, basically, Fb, the magnetic force, is equal to the centripetal force. Okay, the magnetic force is supplying the centripetal force, allowing it to move in the circle. Now, Fb is q times the velocity times the magnetic field, qvb, and Fc is equal to mp v squared over r. Now you can remove one v, there will only be left with one then, so there's still one v left. So you are now left with qb, the charge on the proton multiplied by the magnetic field, is equal to the mass times the velocity over r. So if you want the radius of this circle, okay, they want the wavelength. Okay, so let's calculate the frequency first. Okay, so now we have the radius of the circle. So r is equal to qb, which is on the left hand side, divided by m, mass of the proton, divided by, or rather r was on the bottom, so it will be the other way around. It will be mp v divided by qb. Okay, that is the radius of the circle. Okay, now angular frequency of any motion, the angular frequency can be given by, angular frequency, remember, is just straight velocity divided by the radius, okay, which is the same r there. So we write it rather this side. Therefore, if we substitute into this angular frequency, if we substitute v over this whole formula there, which is radius, it's v over radius. So v over the radius is mp v divided mp, that's the mass of a proton, times the velocity, divided by qb. If we simplify that formula, qb comes on top, the v's cancel, so it will be qb divided by mp, the mass of the proton. qb, so the charge of the proton multiplied by the angular frequency will give you the radius of that circle. Okay, just took a bit of thinking, playing around with your formulas. Now we know, so we have the radius now. So r, the radius of the circle, is qb divided by the mass of the proton, right? Now we know that frequency, this is what we want, is equal to angular frequency did I write there that this is angular frequency, remember? Okay, this is not r, this should not be r. I substituted r there. This should be, remember the original formula should be angular frequency is the velocity divided by r, and then I substitute r. I just wrote the wrong thing there. This velocity was still there, and then the r that we have, remember we calculate r mp V over QB, leaving us with the angular frequency, which is equal to QB. Just the wrong formula, nothing major, MP. Okay, so this is what the angular frequency is. Now we know that the normal frequency related to the angular frequency, the angular frequency divided by 2 pi. Okay, so we will have this angular frequency QB over MP multiplied by divided by 2 pi, and that will give you a formula of the frequency, which is QB over m, the mass of the proton, 2 pi, if I'm not mistaken. And let's check. So that is the frequency, but what do we want? Calculate the wavelength. Okay, now how is wavelength related to frequency? This is the frequency. Now how is wavelength related to frequency in an EM wave? So wavelength is equal to the speed of light divided by the frequency. Frequency. So C divided by the frequency we just calculated, QB over 2 pi mass of the proton. Flip this around, so it's 2 pi C mass of proton over QB. So 2 pi CME. 2 pi CMP divided by QB. 2 pi CMP divided by QB. 2 pi MC, now that M is MP, 2 pi MPC over QB. Let's check A. The correct answer is yes, A. So we have worked out the correct answer, which is now question number 9. A plane EM wave varies sinusoidally, and this is one where it is, I've been trying to, or rather I should have fixed this a long time ago, uh, calculated the, it's in the wrong order. Okay, you need to calculate certain things before you can calculate others. Okay, a plane EM wave varies sinusoidally at 90 megahertz and it travels through a vacuum along the positive x direction. Now, the peak value of the EM field, of the electric field, is 2 millivolts per meter and it is directed along the positive y direction. Okay, you may use the speed of light in a vacuum as 300 meters per second. Find the average energy density in the radiation. What radiation pressure would this wave have? The wavelength, the period, the maximum value of the magnetic field, the average power per unit area. Now, the simplest thing to start with is simply the wavelength, or rather, the period. Let's start with the period. Okay, let's start with the period. Period simply is T is equal to 1 over the frequency. Okay, so it's 1 over, what's the frequency here? 90 megahertz, so it's 1 over 90 times 10 to the 6 hertz, and therefore in seconds it is 1,11 times 10 to the negative 8 seconds. So the period is 1,11. So let's go to the period and choose that option. 1,11 If you rewrite this, it becomes 11,1 times 10 to the negative 9 seconds. And what is negative 9? Nano. Okay, so it's 11.1 nanoseconds. So let's choose that as an option. Now, let's calculate what is next. What can we calculate? Since we have the period and the time, we can calculate the wavelength. Okay, how do we calculate wavelength? Wavelength is equal to the speed of light divided by the frequency. Okay? So, it is the speed of light 3 times 10 to the 8 meters per second divided by the frequency, which in this case is 90 times 10 to the 6 hertz or per second, and that gives you a wavelength of 3.33 meters. So the wavelength is 3.3 meters. Let's see if there's an option for 3.3 meters. Yes, 3.3 meters. Okay. Now let's calculate the maximum value of the magnetic field. The maximum value of the magnetic field, Emax. Remember we had that formula earlier on, which said that Bmax, which is the maximum value of the magnetic field, is equal to Emax divided by speed of light. What is Emax? Do they tell us what is Emax? The maximum value of the peak of the electric field is 2 times 10 to the negative 3 volts per meter. 2 times 10 to the negative 3 volts per meter, and you divide that by the speed of light, 3 times 10 to the 8, and voila, you get 6.67 times 10 to the negative 12 Tesla. This is the peak magnetic field, 6.67 pico. Remember negative 12, so picotesla. Maximum value of the magnetic field is 6.67 picotesla. Okay, another way of writing is just 6.67 picotesla. Okay, now once we're done with the average stuff, now let's calculate the average energy density. Here, the average energy density in the radiation. How do we calculate the average energy density? There is a formula for the average energy density. The average energy density, that's mu by the way, is equal to half mu naught times E max, E naught max, the peak value for the magnetic field. We could have actually calculated this first. I just calculated the simplest stuff first. Multiplied by the permittivity of free space, 8,85 10 to the negative 12, multiplied by E naught. And what is E naught in this case? It's the maximum value of the magnetic field, which is 2 times, we just wrote it down, 10 to the negative 3. We remember it's millivolts, and that is squared. Work all of that out. We should get 1,77 times 10 to the negative 17 joules per cubic meter. Now let's check the energy density in the radiation. 1,7 times 10 to the negative 10 joules per cubic meter. There we have it. Okay, the next thing is the average power. Okay, I calculated the average power. Then average power is nothing but, the reason why I calculate average energy density first is because I need this value for the average power per unit area. Now the average power per unit area, in this case is nothing but the intensity. Okay, the average power per unit area is the intensity. So the intensity is just the average energy density that we just calculated multiplied by the speed of light. Okay? Remember we had it earlier on, the average energy density is I over C. So it's just 1,77 times 10 to the negative 17 multiplied by the speed of light, 3 times 10 to the 8. That provides us with an answer of 5.31 times 10 to the negative 9 watts per meter squared. That is the intensity, okay, the average power per unit area. So the intensity is 5.3 times 10 to the negative 9 watts per meter square. What is left to calculate is the radiation pressure. Well, let's go back to the radiation pressure. We have calculated here radiation pressure is equal to 2IC. This is my perfect reflector. Remember, it's in vacuum, so it's 2I over C. So it's 2 times the intensity. You see, some of them you need to calculate before other. So I had to calculate average energy density. The rest I could calculate at any time, but the others, like the average power per unit area, is based on the average energy density, and the average radiation pressure is based on the average power per unit area. This is times the intensity, 5.31 times 10 to the negative 9. It's still on there. I just chose it. There it is, the last one I just chose. Over the speed of light, 3 times 10 to the 8. And that, ladies and gentlemen, gives you an answer of 3.54 times 10. My throat is getting dry. Times to the 17 Pascal. Remember, we're still pressure and it's in SI units. So 3.54 times 10 to the 17 Pascal. And that is everything. This problem, please note this problem. It does come out a lot because here you can get 2, 4, 6, 8, 10, maybe basically 10, 8 to 10 points on that question. I would make this one, remove these two, and then the rest, each one 2 marks, and then wonderful marks. You see there, we correctly calculated each one of those values, or rather we chose the correct answers. Okay, very last question. A light ray whose frequency is 6 times 10 to the 14 hertz in a vacuum is incident on water which has a refractive index of 1.3. Then the wavelength of light after it enters the water is in nanometers is. Okay, now refractive index, remember, is just the wavelength in a vacuum. In terms of wavelength, the refractive index is wavelength in a vacuum divided by wavelength in water. Okay. Usually we do this with the speeds. You can also revise it for wavelengths, which is what I did in this case. Okay, as you can go and check for yourself. Just put the speeds there. Wavelength is equal to speed divided by frequency. The frequency stays the same. Therefore, the wavelengths will change as the refractive index change. Remember, refractive index is defined as, okay, let me just derive it for you, show you how it's done. N is equal to the speed of light in a vacuum, the speed of light in a vacuum, or rather, yes, speed of light in a vacuum divided by the speed of light in the water. Okay? Now, what is speed? It is nothing but the frequency multiplied by the wavelength in a vacuum times the frequency multiplied by the wavelength in the water. Okay? Now, the frequency of this light, its oscillation frequency does not change. Therefore, the wavelength in a vacuum over the wavelength in the water will give you the refractive index. So back to our original formula that I wrote there. And the refractive index is equal to wavelength in vacuum divided by wavelength in water. So we want the wavelength in water, so wavelength in vacuum divided by the refractive index. Now what's the wavelength in vacuum? It is, we have the frequency in vacuum, so we can calculate the wavelength in vacuum. Okay, the wavelength in vacuum is nothing but the speed of light divided by the frequency, because we've been given the frequency, divided by n. So n is the refractive index, 1,33. The speed of light is 3 times 10 to the 8 divided by the frequency that they give us, 6 times 10 to the 14. That, ladies and gentlemen, will give you the wavelength in water. And the answer in water is, the wavelength in water is 3,6, or 3,76 rather, times 10 to the negative 7 meters. Or if you move it along, it is 376 nanometers. 376 nanometers. 376 nanometers. Let's check there. 376 nanometers. And it is in, yep, that is correct. Okay. Now, ladies and gentlemen, that is all that we have time for today. And I hope that you get some value out of this tutorial session. All the best, and I will see you later on. Thank you.